All right, this is our second lecture on heat exchangers. We talked about different types of heat exchangers. We covered the overall heat transfer coefficient. We moved into, or we talked a lot about the EBs, energy balances, don't forget that, and then our rate equation. And I alluded to log mean temperature difference, but I didn't derive it, did I? And so we're going to pick up there, talk more about the log mean temperature difference, and then move into a method that is like a second method. The first method for analysis of heat exchangers would be the log mean temperature difference method. And then the next method for analyzing heat exchangers is the effectiveness NTU method. We'll get into that. So this LMTD method, log mean temperature difference. Well, I like to put it in this, I'm going to derive it in a second, but think about concentric tube heat exchanger, tube inside of a tube, right? And we could put counterflow, that's typical. So the fluid that maybe in the inner tube is flowing one way and the fluid in the annulus is flowing another way. We like to just plot it as a function of distance x from 0 to L, from one end to the other end of a finite length concentric tube heat exchanger. And maybe the temperature hot comes in over here, goes out, and the temperature cold comes in at this location and goes out there. We've talked about that. True. One thing that we need to make sure and not forget is that we can do an energy balance for the total system, a global energy balance. A global, if that makes sense. From one end to the other end, from inlet to outlet. So from the perspective of the hot fluid, you could write Q is equal to cap C of the hot fluid, temperature hot in minus temperature hot out. What was cap C? Heat capacity rate, and it's the product of the mass flow rate of that hot fluid times the specific heat constant pressure of that hot fluid. Heat capacity rate. Where did this equation come from? Energy balance. Control volume just around the hot fluid. And what is Q? Q is the rate of heat transfer out of the hot fluid. Where is it going? To the cold fluid. We can also write a global energy balance from the perspective of the cold fluid. Now, we don't like to change signs, so Q is both positive out of the hot as well as into the cold. Same Q, maybe 50 watts, 500 watts, 2,000 watts, whatever it is. And it's the heat capacity rate of the cold fluid. And this is a little tricky. I got two options. Do I put temperature cold out minus temperature cold in, or do I put temperature cold in minus temperature cold out for that temperature difference? I'll start with my first clicker question, answer A or answer B. You could change your answer if you like. So let's ask this. What's happening to the cold fluid? It's heating up. So which is the higher temperature? The cold fluid out. So the cold fluid out is greater than the cold fluid in. And we like to talk about a positive number times a positive number equaling a positive Q. This Q and that Q are the same. Oh, look at that. I'm going to stop it now. No, it's 100% correct. I am doing better as an educator. Just be careful. Every now and then I can write that wrong. I can write it incorrectly. Okay. The other one is not an energy balance. Both of these are energy balance statements. One is a rate equation for the total system. The rate equation is Q is equal to U times A times appropriate delta T that derives it between the hot and the cold. That delta T is like an average delta T for the whole heat exchanger. Well, what is that average delta T? It's the log mean temperature difference. It's that, why didn't they just call it the average temperature difference? I don't know. I mean, look at the definition of it, right? Look, how is delta T log mean defined? Well, they take the temperature difference on this end, call that delta T1. What is delta T1? The temperature hot in minus temperature cold out. And they take the temperature difference on this end, temperature hot out minus temperature cold in. And they use those delta T1, delta T2 to compute delta T1 minus delta T2 divided by the natural log of delta T1 divided by delta T2. We're going to derive that in a minute. But what does it represent? You can get bogged down in the math. It just represents that average temperature difference between the hot fluid stream and the cold fluid stream throughout the heat exchanger. Well, to derive it, we have to not work just on a global basis. We have to work on a differential. And we can write the same type of equations on a differential format. What's differential? Consider a little x plus dx. So this is a little distance dx, or delta x. What's happening just in that little dx? Well, we could say there's a little amount of heat transfer. dq, small amount or small rate of heat transfer, it's equal to, just look at the analogy here, it's going to be the mass flow rate of the hot, specific heat of the hot. Well, let's just replace that by cap C of the hot, times not the global temperature change, but just the local temperature change. So you think about it in a minute, and I'm going to put dx here. I'm going to put dth dx right there. Can you see that that really, when I multiply the derivative of the temperature profile, the hot temperature profile times dx, that gives me a small change in the hot temperature. And I left a little room right here because it can be a little confusing. And what did I just put in red right there? A minus sign. Now, why did I put a minus sign in there? You go back to slopes in calculus. You know, if somebody said, here is my function f as a function of x, and the line looks like that, and somebody says, what is df dx? Is it positive, equal to 0, or negative? What would you say? It's positive. Somebody says, no, f is a function of x, so it looks flat. What would you say? It's 0. Somebody says, sloped like that. What is df dx? Negative. Look at the slope of the red line. I'm increasing x. The temperature, the high temperature, TH, is going down with the increasing x. That's why I need a negative sign. So a negative times a negative is a positive quantity. Everything in that equation is positive. All right, now it gets even a little trickier because let's do it for the cold. That's into the cold. A small amount of rate into the cold. That's equal to the heat capacity rate of the cold fluid times dx. Now I've got to figure this one out. dt cold dx. But do I need to put a negative sign here? Yes or no? I'm going to pause because I really want you to think about it. I'm going to walk around and see what you say on your sheet of paper. Do you understand my question? Is the coordinate system still for both of those curves in the positive x direction? Yes or no? I didn't change coordinate systems and said, oh no, when we're going to now talk about, this function, no, I'm going to put the x now in the positive at direction. No. The positive increasing x is to the right, true? For both of these curves. So if somebody says, what's the slope of this curve? Would you say positive or negative? Negative. Somebody says, what's the slope of this curve? Positive or negative? Negative. So if I want this whole thing to be positive, this is definitely positive, that's positive, this has to be positive. Don't I need the negative sign? But why did a lot of students say, no, I don't think I need the negative sign? Because they're thinking about the direction of the flow and not just the slope of a line. They're thinking this is the direction of the hot fluid flow in the positive x direction. I agree. And then this is the confusing part. What is the direction of the flow of the cold? It's in the negative x. But we're just saying, what is the dt cold dx multiplied by a little positive change in x? I don't know if that helps. Did that help? I just keep talking until hands go down, and then students forget their questions, and then I can move on. Did you have a question?
Yeah, I was just wondering why cap C was positive, because the mass flow rate is negative.
But it's a positive mass flow rate, and it could be in the counterflow or in the parallel flow orientation. We never changed the flow rate. Yeah, that could be a trip up too. Like, do I have a direction on m dot? No, there's no real direction on m dot, just the magnitude. Okay. Then we have this equation. What's the analogous for the rate? Well, we have dq is equal to overall u dA th minus tc at that location. Not thn minus tcn, no, just at that location. So at that location, I have some little temperature difference that drives that rate of heat transfer at that location. So what is this area? Well, we like to write it in terms of a little dx. So we put a p dx. All right, now I'm really confused. What is that pressure doing in this equation? Is that pressure P? No, it's recycled P. It's going to be for the perimeter. The perimeter. So a perimeter dx gives me a little area. And what was this big U again? I forgot the name. Overall heat transfer coefficient. That's right. So what we can do to derive this equation, we can start here and work the math and get a differential equation. And so let's press forward. Here's the derivation. So you have the counterflow concentric tube. You have all this temperature hot in, temperature hot out, temperature cold out, temperature cold in. Actually, I have, this is the wrong direction on that one. This is the direction, temperature cold in, right? Now I fixed it. Little dx like we just talked about. What is this equation? 1, 2, 3. Hey, your old friend, previous slide. True? And then we take equations 1 and 2 and 2 and 3 and we combine them. Then we subtract them, and we're up here already. And then we just recall from the global energy statements these two equations. So you can rewrite to get 1 over cap C of the cold, 1 over cap C of the hot. Use that to put right here and right there. And voila. I didn't say the math was pretty, but it is just math. And then you look at this equation, and you can go from here to here. What did we do there? Separated, put the dx over there, put the changes in the temperature there. What do we have here? What did I just do? Integrated. This is my new equation. Rearrange, and you get that the overall Q is equal to UA times an appropriate delta T, and that is the log mean temperature difference. That's how you get the definition of the log mean temperature difference. I tried to make that as easy as possible, but it is a lot of math. All right, let's press forward. I want you to take this equation, or should I have written it that way? Which one is correct? Is side A correct, or B correct, or both correct? The both are correct, right. There's a relationship that the natural log of 1 over A is equal to minus the natural log of A. Do you remember that one? Yeah. So that's what's used between these two right here and here. Anyway, somebody says delta T1 is 30 degrees, delta T2 is 50 degrees. Calculate, use your calculator to calculate the log mean temperature difference for this problem. I'll pause, walk around, see what you get. So a lot of you already had it. So you put the 50 minus 30, and divide by the natural log of 50 over 30, and it comes in. But who didn't have a calculator and just looked at the two numbers and said, you know what, I think it's going to be around 40? You know, students are pretty smart. That's right, it's around 40. It's kind of an average delta T for the heat exchanger. But this will work for a lot of different cases. Some cases like this, it's easy to think, oh, that should be around 40. Let's go to another one. Somebody says, same, I want you to calculate the log mean temperature difference when it's 30 and 30. First of all, an engineer student without the calculator, what do you think the average delta T is going to be? What should the answer be? 30. Jump on your calculator. Let's see what we get. All right, so what happened? How many people got 0 over 0? Yeah, so do this. Do this to see now. Do this as 30 and 30.001. Try that. Just try it. Let me know what you get. All right, so when it's precisely 30, 30, it seems to give a problem, but if it's just 30 plus a itty bitty bit, it comes back with 30, true? So if you just put in 30, 30, you typically it runs into trouble. So what's going on? How many people are thinking back to those glorious days when you first came into university, you were taking Calculus 1? Oh, it was so fun. You learned such incredible things, and you recall right now from Calculus 1 a particular method that could be used for this challenging problem so that you could find out the answer. It's limits. Yeah, that's one of the words, limits. La hospital, la hospital, or however we want to butcher it, because I don't know. I never met the guy. So, yeah. So what we do is we go back and we try to figure out how are you going to do the special case when delta T1 is equal to delta T2. And what you do is you say, okay, well, let delta T1 be delta T1, but let delta T2 be delta T1 plus a little epsilon, and then I'll do the limit as that epsilon goes to 0. And what I should find is the limit as epsilon goes to 0 of my log mean temperature difference, which would be delta T1 minus delta T1 plus epsilon divided by the natural log delta T1 divided by delta T1 plus epsilon. The limit of that as it goes to 0, L'Hopital's rule, is going to be delta T1. There's a few steps in this ... How many people kind of remember the gist of it? What was the idea behind it? You remember? Yeah. So if the limit as x goes to something, 0, it doesn't have to, x can go to a. But if you have f of x divided by g of x, and both f and g go to 0, or they can, I know they generalize these things, they could go to infinity or this and that, but let's just consider the simple case. They both go to 0. Then that would be the equivalent to get f prime and g prime and try again limit as x goes off to 0. True? Anyway, you can do this. This is great. Maybe they should have had this in your Calculus 1 exam. This is when it's really useful. Well, I'm not going to do it. I did it in 8:30. And I'm tired. Let's press. Let's move on to more interesting stuff. What did I sketch here? Temperature is a function of x. True? Temperature is a function of x. What's the red line for? The hot fluid. Can you tell what is the direction of the flow of the hot fluid? Is the hot fluid flowing to the right or the hot fluid flowing to the left? Just from the profile. To the right. Because it's going to be cooling. And then how about the cold fluid? What direction is the cold fluid flowing? Has to be just from the profile. Is this heat exchanger a counterflow, parallel flow, or I don't know? All right, I'm going to go ahead and stop this. I still have one person incorrect. Oh, I had two then. One quickly jumped on the wrong bandwagon. When one fluid's going to the right, the other to the left, that's counterflow. All right, here's another question. This heat exchanger, can you tell just by looking at the shape of the hot fluid temperature profile, the cold fluid temperature profile, is it counter, parallel, or I don't know? This would be a very interesting study to see how people respond because, perfect. What can I say? That's nice. So the blue is moving in this direction. It's being heated as more heat's being transferred to it, and the hot's being cooled as it flows in that direction. All right, if the mass flow rate of the hot, I think we did this last time, didn't I? Mass flow rate of the hot is increased. Will the log mean temperature difference change? This is a counterflow heat exchanger. I will go ahead and show the results. And you could still change your answer as I talk about it. So we did this where the hot fluid really is blowing through the system, and then the temperature profile for the hot, there'll be less and less change in the hot's outlet temperature. The temperature of the hot outlet will increase. It'll get closer to the temperature hot inlet, won't it? If you just blow the mass of the hot fluid flow through there. Now, what that's doing is it's opening up this temperature profile between the two fluid streams. You're going to then think about the rate equation. Q is equal to UA delta T log mean. So you think about, well, you're kind of opening it up. They're spreading apart. You are going to increase the Q, which means the blue is going to come up too. It's going to come up as well. But overall, you're opening it up. There's going to be a larger Q, a larger log mean temperature difference. Now it's time to grade. True? So I am doing well. We got pretty good. It will increase. How about this next question? If the mass flow rate of the hot is increased, how will Q change? I just answered that. Let's move on. Let's solve this problem. We have a concentric tube heat exchanger with thin-walled inner tube. When you see a thin-walled inner tube, basically there's no conduction, negligible resistance to conduction through the wall of that tube. Negligible difference in diameter for that thin-walled inner tube. It operates in a counterflow mode with this inner diameter and that outer diameter. Water at this flow rate and this temperature enters, and oil at this flow rate and this temperature enters the annulus and exits at that temperature. So what is the hot fluid? Is the water the hot, or is the oil the hot? The oil is the hot fluid, and the water is the cold. You almost need to write down sometimes the obvious. And then the temperature of the hot in is given. That's 130 degrees C. The temperature of the hot out is given, 70 degrees C. The temperature of the cold in is given, 25 degrees C. The temperature cold out, is that given? No. But we're given the mass flow rates. I'm not going to repeat those, of the water and of the oil. And we look down here and they give us a bunch of properties for water and oil. And you're probably thinking, I need to get that specific heat. You're right. So they give us the specific heat of the water, which was the cold, and the oil, which is the hot. Okay. The overall heat transfer coefficient, U, is given. Oh, that's kind of nice. Makes it easier. I don't have to go in from first principles calculate U. Calculate the rate of heat transfer in this heat exchanger. What is my appropriate symbol that I'm looking to solve for part A? Q. What would be the units, anticipated units for my answer for part A? Watts or kilowatts. How would I solve for it? You can think of energy balance from the hot, energy balance from the cold, or the rate equation. Energy balance for the hot fluid. So if you do the energy balance for the hot fluid, Q is equal to the heat capacity rate of the hot times the temperature hot in minus temperature hot out. And this heat capacity rate of the hot fluid is the mass flow rate times specific heat of the hot. The mass flow rate of the oil, 0.1 kilogram per second times the specific heat of the hot fluid, 1900, joules per kilogram Kelvin. Do the kilograms go? And we're left with 190 watts per Kelvin. True or false? Thumbs up? You like it? Yeah, thumbs up. So now we can just put in Q is equal to 190 watts per Kelvin times 130 minus 70. Oh no, these are degrees C. I'm going to have to do it. Come on, we've done this before. True? Yeah, temperature difference. And so we calculate the Q, and I forget what it is. 11,400 watts, box it. Okay, part B. What is the outlet water temperature? Well, that's right down here. What is the cold outlet temperature? How do I solve for that one? Energy balance for the perspective of the cold fluid. So we go back to the energy balance for the cold fluid. We find Q is equal to the heat capacity rate of the cold, temperature cold out minus temperature cold in. So the temperature cold out is equal to temperature cold in minus Q divided by heat capacity rate of the cold. It's not a minus, it's a plus. So we calculate the heat capacity rate of the cold. The heat capacity rate of the cold is the product of the mass flow rate 0.2 times 4200. So that's 840. What are the units on that? Watts per Kelvin. Did I do that right? Okay. So the temperature cold out is 25 plus 11,400. I'm going to drop the units right here, 840. So the temperature cold out comes in at 38.6 degrees C. Did I use anything other than thermo 1 and energy balance? No, not yet. Finally, we get to some heat transfer for part C, something new for this class. So what is the length of that heat exchanger? Well, you think, really they're asking you about the area. Because isn't the area of the heat exchanger equal to pi dl? What's pi d? The inner diameter? Pi dl. So how am I going to find how big it is in order to achieve that heat transfer? I use my rate equation, which is Q is equal to UA delta T log mean. I know the inlet, I know all four temperatures, inlet, outlet of both fluid streams. And so in the interest of space, delta T log mean comes in at 65.5 degrees C. You're given the U, you already know the Q. I need to calculate that area. The area comes in at 1.58 meters squared. Hence, the length is the area divided by pi d inner is 20.2 meters. I tried to keep it on one page. Look good? All right. Now let's move to the other method. Sorry, did everybody get the notes on this? All right. So let's move to the effectiveness NTU method. Well, let's just sort of put the pieces of the puzzle down. The actual rate of heat transfer. What symbol is the actual rate of heat transfer occurring in our heat exchanger? What do we use for that? Q. All right. Then you also have to define a maximum rate of heat transfer. This is as if the area of the heat exchanger went off to literally infinity, and it was a counter flow heat exchanger. So maybe up here I sketch and I think, I'm coming in with the hot fluid, T hot in, and maybe over here I'm coming in with the temperature cold in, right? And this is x, but if I have a finite L, but if I go like symbol like this, oh, I'm going to cut it, like this, and then I can make a very, very long x-axis. There's like, I should maybe draw like 3 of these because it depends on the heat capacity rate of the hot and the cold fluid, but the hot fluid could come out the same as the cold in, and the cold could be like this, or I hate to try and repeat this. Let me try and repeat it. Edit, copy, come on, copy, paste, paste. All right. Or the temperature of the cold could do something like this. It could come up like very close to the hot, and the hot could be something like this, right? Or the special case, which doesn't happen much in practice. All right? You see that? One of the fluids experiences a maximum change. Okay? For this case up here, the first case, what fluid experiences the maximum change? The hot. The temperature hot in is the highest of the high, and it goes out the temperature of the cold in, doesn't it? All right. Over here, for this other case, it's not the hot fluid that goes through the maximum temperature change, it's the cold. In that case, what is the maximum temperature change? Well, the cold's going out at hot in, and the came in at cold in. And in either one of them, for this one, it's temperature hot in minus temperature cold in. What's the same in all 3 of these? The maximum temperature change of one of the streams of fluid. All right. So to talk about the maximum rate of heat transfer, we have to talk about the maximum temperature change. And so the maximum temperature change is just T hot in minus T cold in. Okay. We're going to have a heat capacity rate of the hot fluid, and we're going to have a heat capacity rate of the cold fluid. C cold. For this first case, the top case, which one is the minimum and which one is the maximum? Which one has the smallest heat capacity rate, the hot fluid or the cold fluid? Which one has the smallest heat capacity rate? The hot fluid, doesn't it? Because if the Q out of the hot is equal to the Q into the cold, the heat capacity rate of the hot times the temperature hot in minus temperature hot out equal to the heat capacity rate of the cold, temperature cold out minus temperature cold in. So you look at the first case and you say that they have to equal each other, and this is the largest delta T. This is smaller delta T, isn't it? Just compare these. This is smaller. Hence, this has to be smaller of the other one. So this is the minimum. This is the minimum heat capacity rate. How about for the second case? Compare the heat capacity rate of the hot fluid, the heat capacity rate of cold fluid. Guess which one is the minimum? The cold fluid has a minimum heat capacity rate. I'm going a little fast, but maybe think about it when you're reading the text and studying. And then here, well, guess what? Both of them are equal, and so neither is minimum or maximum. They're both equal, so I guess the min is both and the max is both. All right. So what you have is the minimum heat capacity rate. So the maximum rate of heat transfer occurs when you can work out the equations when its area goes off to infinity, or think about the length goes off to infinity, and it's a counterflow configuration, and you get Q max is equal to the minimum heat capacity rate times the temperature hottest of the hot, well, that's hot in, minus the coldest of the cold, that's the cold in. That's the delta T max. So the minimum heat capacity rate is just like it sounds. Just find both of the heat capacity rates, MIN, and then just do, is it either the hot or the cold? Just calculate the min of either one of them. Make sense? Okay. Now we get to finally some effectiveness and then NTU. So what is the effectiveness? It's this symbol right there. What does that symbol look like? Epsilon, Greek. You're learning Greek. That's right, epsilon, and it's the ratio of Q divided by Q max. That's the definition of the effectiveness. Did we already define Q max? Did we already define Q? Sure. So effectiveness, and then number of transfer units. They just abbreviate NTU, all caps. All right, what is that? UA divided by C min. What is U? Overall heat transfer coefficient. What is A? Area. What is C min? Minimum heat capacity rate of either the hot or the cold fluid stream. So, people have figured this out a long time ago, that you can analyze parallel flow, counter flow, cross flow, shell and tube, all kinds of heat exchangers, and you get relationships where you can get the effectiveness as a function of the number of transfer units and a ratio of CR is a ratio of minimum to maximum heat capacity rates. Maybe I should have put that in. CR is equal to C min divided by C max. If C min is equal to C max, the ratio is 1. But it'll only get less than 1. It'll go from 1 down to 0, CR. As well as you can work, a lot of people have worked it out, you can get a relationship where the number of transfer units is a function of the effectiveness and CR. This looks like a lot of math, but it's really gold. This is really good, because these really represent two challenges or types of problems when doing heat exchanger analysis. One is we want to size the heat exchanger. Answer the question of how large of an area do I need for the heat exchanger to accomplish the goal of moving this much heat from one fluid stream to the other fluid stream, the rate of heating. The other problem is you're given a particular heat exchanger. Its size is already fixed, and you may know your inlet and your temperature streams and your flow rates, but what you want to do is you want to rate it. You rate the heat exchanger, which is basically answering the question of how large of a Q can I accomplish in that heat exchanger. Not how large the area needs to be, that's sizing the heat exchanger. How large is the Q? What is the rate of the heat exchanger? Those are the two basic questions in heat exchanger analysis. Pretty easy, isn't it? It's just getting these relationships of the effectiveness as a function of NTU and ratio of heat capacity rates, or the size NTU as a function of effectiveness and heat capacity rate. Well, aren't you glad somebody did that work already? Tabulated a lot of it? So you'll look at the table, and each one of these in table 11.3, what is the desired output? It's on the left. It's your effectiveness. What's all over here? Crazy equations as a function of NTU and the ratio of heat capacity rate. Oh, you have parallel flow, you have counter flow, shell and tube, cross flow, blah, blah, blah. Different categories, configurations, and conditions. Some of them don't look too pleasant. Aren't you glad a graduate student did it before? Or maybe a faculty member, maybe? Published it? There's another table where the NTU is equal to a function of the effectiveness as well as CR. Well, let's go ahead and derive at least one of them. Guess what? more math. And this one's just as tricky as the derivation and the log mean. What you do is you can just have to pick a configuration, work it out. Concentric tube, counterflow. Just pick it and work it out. All right. So we already know this is true, this is true, this is true. You can assume that one of the fluid streams is the minimum, work it out, go back, assume the other one is the minimum, you'll get the same answer. So you just maybe pick the hot as the minimum. Then you have Q max is C min, the delta T max, that we already worked out. This is the definition of the effectiveness. I can roll that into an energy balance right here to calculate the actual Q, unraveling the effectiveness. Get the hot out. Use these definitions of the ratio of heat capacity rates for the assumption that the hot is the minimum. Get an expression for the cold out. Get an expression for delta T1, delta T2. Put them together in the log mean temperature difference and get this out of the way. It's always in my way. There's some cancellation and some algebra, pretty serious, to come down here. We recall our previous, you cancel even more, and you get a relationship like that. I didn't say it was easy. I thank the people that went before us, that did it and published it. All right. You can then compare that to table 11.4. I only copied a part of that table in there. Here we're getting the size as a function of our effectiveness and ratio of heat capacity rates. What we just derived is the same as what's in the table. You could take that equation and manipulate it and flip it such that you now have effectiveness as a function of the other, NTU. Again, just algebra, and then compare it. Yep, it's the same. So table 11.3 for counterflow, there it is. I didn't say it was pretty, but the hard work is getting those relationships. Let's solve a problem. Same exact problem, now not using the log mean temperature difference, but using the effectiveness NTU method. So you would not have any difference. This is the same problem we just solved. In part A or part B, the answer and the strategy is the same. Remember, only in part C did we really analyze the heat exchanger. So for part A, what did we get for our answer? It's 11,4. Yeah, so Q is equal to 11,400 watts. And the outlet temperature, temperature cold out, is 38.6 degrees C. How do I find the length of the heat exchanger? Well, is that asking us to calculate the area? Yeah. So the general relationship we're going to be doing is we're going to say NTU as a function of the effectiveness and the ratio of heat capacity rates. All right. I already know what Q is, so the effectiveness is Q divided by Q max. It's like, I know that one, 11,400. What is Q max? Well, I have to do a little work. Q max is equal to C min times temperature hot in minus temperature cold in. It's like, oh, I know the hot in and the cold in, but the minimum heat capacity rate. Well, we go back and compare. The C min was 190 watts per Kelvin. C max was 840. And so I can calculate Q max, which is 190 watts per Kelvin times the temperature difference. The hot coming in is 130 minus the cold coming in at 25. And the Q max comes in at 19,950 watts. Let me pause. If you have a calculator, can you run that and verify? And if you do get it, give me a thumbs up. Good, thank you very much. Appreciate it, thank you, thank you. So now we can come back and we can calculate that effectiveness. That effectiveness, if you can calculate it with me, 0.57143. Yep. That means if I decided to go all out and buy a huge, huge heat exchanger, I could get, for those inlet conditions, I could get 19,950 watts, but I'm only getting 57% of that. That's my effectiveness. All right, for a finite size heat exchanger. All right, so that's my effectiveness. So I go, maybe I have it on this slide. Yeah, I do. So I know my effectiveness. I didn't calculate CR, but that was 190 divided by 840, which is 0.2262. So the C sub R, the effectiveness, don't make an error, and the number of transfer units comes in to be 0.91611. What was the number of transfer units? It was UA divided by C min. Hence, the area is the number of transfer units times C min divided by U. And for this problem, the area comes in 1.5824 meters squared. And that area is pi d inner L, hence L is equal to area divided by pi d inner, and the L comes in at 20.15 meters. It's the same answer, 20.2. So that's good. They're not independent methods. I mean, they look very different, but they have the same math. They conserve energy. The rate equation's there. So we've exposed you to both the log mean temperature difference and effectiveness NTU. This is the preferred method out there. You can very easily rate it as well as size it using the effectiveness NTU method. All right, in the last few minutes that we have, I'd like to ask this clicker question and then talk about it. So for this problem right here, we have that the temperature hot in looks pretty flat. And actually the temperature hot out is equal to the temperature hot in. Why is the temperature hot out equal to the temperature hot in? Is it because the cold fluid is condensing, the hot fluid is condensing, the hot fluid is boiling, or the cold fluid is boiling, or I don't know. So we'll just go ahead and talk about it a little bit here. So let's do this. One of the two fluid streams is undergoing a change of phase, because either boiling or condensation is a change of phase, isn't it? And if the general assumption is, I forgot to stress it, is that the pressure on the cold side is about constant and the pressure on the hot fluid side is constant. There's not a big pressure drop that the hot fluid experiences. The heat exchanger is not a pressure drop device. It's a heat exchange device, and it does come with some modest pressure drop. Anytime you force fluid through a real component, there is some pressure drop. But our underlying assumption is a good heat exchanger has minimal pressure drop. Some of them have more than others, I agree. But think that there's negligible pressure drop on the hot and negligible pressure drop on the cold. Okay. With that, one of them is changing phase. Which one is changing phase? Is the cold changing phase? No. It's basically what they call the sensible heating. Meaning, as more heat is transferred into the cold is actually heating up as it flows through the system. It's sensible. It makes sense. The latent, the hidden, is associated with a phase change. So right away we could say it's not the cold condensing, and it's not the cold boiling. So okay, A and D have properly been abandoned. All right, and so it looks like we're piling up on B. So the hot fluid is condensing. True? What if I said the hot fluid is boiling? That's probably easier for you to understand because you think about a pot on a stove. Do I put heat into the fluid? Do I put heat into the bottom of the pan to make the hot fluid boil? Yeah, right. You turn it around. In order for the heat to come out of the hot fluid, it has to condense, doesn't it? So here, the right answer is B. Hey, good job. Keep talking like that. So there you go. So we're 100% correct. So the hot fluid is condensing. Okay. What is the specific heat effective for the hot fluid that is condensing? I think that's my next question. Yeah. What is the effective specific heat of a fluid that is condensing? Is it positive infinity, 0, negative infinity, or I don't know? Well, what we'll do is we'll talk through this one too. What was the definition of C sub P from thermo? Hey, that was more than a few weeks ago. How am I supposed to remember definitions like this? The rate of change with respect to temperature holding pressure constant of something. The rate of change of something. What is that something? The rate of change of internal energy or enthalpy? U or H? H. True? All right. Could you have, let's talk about water for a minute, H2O. Can water exist in the liquid state? Yeah. Can water exist in the vapor state? Yeah. Let's talk about a plot at 1 atm. That's a special atmospheric pressure, and we could talk about as a function of the temperature. You could talk about the enthalpy of water, and then something happens right around 100 degrees C. What happens to water right around 100 degrees C? There's a phase change, and we have the enthalpy of saturated vapor, and we have the enthalpy of saturated liquid, saturated vapor. Isn't there a huge increase in the enthalpy as it moves from the left side to the right side of that line? So what was over here? What state was it at, and what was over here? Over here, it's at a temperature less than the boiling point, and so it's in the liquid state, and over here, it's in the vapor state. True? Okay, so what you could have is if I cool it, I get lower and lower enthalpy. The enthalpy goes down as I cool it. What is the slope of this line? Look at the definition. The rate of change of enthalpy with respect to temperature holding pressure constant. Isn't this C sub P of the liquid? Yeah. And then what about this one over here? You have a little slope of the line because I could continue to heat it and it's a vapor, and the enthalpy would go up above the H of G. So what is the slope of this line? C sub P of the vapor. So did that help us? Let's take a look at how people have answered this. No, not really. What is C sub P? Slope of that line. We're let's do this. Let's nudge it a little bit, put a little here and a little there, and maybe like that. Is the slope of this line large negative or large positive? Large positive. Let's tighten it up a little bit. All right. I'm going to have to call it quits. All right. Some of you just don't get it. It's a positive infinity. No, for this specific heat, C sub P. The specific heat. What was C sub P? The slope of that line. I know that was a challenging question. Oh boy, I'm going to stop. So anyway, when you take a look and you have C for the hot fluid, if it's changing phase, guess what? It goes off to infinity. It is not the minimum. The other fluid is the minimum. You could use the effectiveness NTU method. You just have to know that the heat capacity rate of any fluid that's undergoing a phase change is big. Big. It's not the minimum. And this method will work. Okay? Do you want to try this one? Forget it. It really does. They're both the same. They're both positive. They're both positive infinity. All right. Well, with that, I'm done with the heat exchanger analysis. We'll see you next time.